Hopscotch, Farmer John's cows are going to be playing a game of hopscotch. So it's going to be an R by C grid, and a cow is only able to jump from one square to another if the other square is at least one row and at least one column below, and the colors or the values given in the input are different for both squares. So we want to know the number of ways that we can jump from the top left square to the bottom right square, and then mod this value. Let's go look at the algorithm of this question. We can solve this question using a 2D DP. So if we have a square like this, we can actually make a subgrid of all of the valid places to reach it. And that's just going to be the subgrid that's one column up and then one row back. So anything in here, as long as it's a different color than this point, is able to jump to this point. So for example, if this square is pink, then this green square, these are able to jump here, this yellow square is able to jump here, but this pink square here is not able to jump since they're the same color. When we create our 2D DP, we're going to assign it as dpij, where dpij is going to be equal to the sum of all of the ways to go from dpxy to dpij, granted that the ij and xy follow all of the conditions. So that would be the x is less than I, y is less than j, and then the color of xy is not equal to the color of ij. So to find the value of dp this point, it would just be the number of ways from here to here, and then here, 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 and then so on and so forth, for all of the squares inside of this subgrid, excluding the ones that have the same color. And what that means is we can translate this, so dpxy, where xy is fulfilling these conditions, into the equivalent, which would be dpxy, where x and y are inside of this subgrid, minus the number of values of dpxy where the color is the same. So in order to find the number of ways that we can, or the number of grid values that have the same amount, so that have different colors but are in this grid, we can just do the total number in this grid minus the number of points or the number of values that have the same color. So that's dpxy here minus dpxy here. So if we were to just brute force this question, that would be it. But in order to make it faster, what we can do is we can use a 2D range query to find the number of values here and to find the number of values inside of the square with the same color. Instead of having to loop through every time to find those values, we can just keep a two-dimensional range query from here to ij that's going to store that number. So this value here can be found using a 2D range query, and this value here can also be found using a 2D range query. So what we're actually going to do is we're going to store a 2D range query, or a range query for all values or all colors, and that's just going to, no matter what point we are in the grid, it's going to let us find the value in this box, or the total sum. And then we're also going to store a 2D range query for every color, and that's going to allow us at any point to find the number of values or points with the same color. When we store 2D range queries, well, in order to find the number of ways to go from, say, this point to this point, it's just going to be the number of ways here, so dpxy, and then added it to here. So our range query for everything is just going to store the value of all of the DPs, so the sum of all DP values in this range, and then for every color, it's going to store the sum of every value with this certain color, and then that's going to be in the range query. So to find the sum of all of the values that have a different color, it'll just be the sum of the total DPs minus the sum of the individual color DPs. The other thing we can notice is a 2D range query is going to be too expensive. And to optimize this, we can use a one-dimensional column prefix sum. And the way that's going to work is we're going to iterate from left to right. So we're going to be iterating down, and then we're actually going to be iterating from columns right to left. And that's just because when we do this later, it's going to be able to give us the accurate values, since we'll be using the old DP values and we won't overwrite it. But basically, we're going to be using a column prefix sum. So as we go from the top rows down to the bottom rows, we're going to continually update this one-dimensional range query. So we're going to be looping like this. And then once we have this row done, we're going to take this value, update this value, take this value, update this value, take this value, update this value, and so on and so forth. And then once we have our 1D range query for row 1, we're going to keep iterating down to row 2. So we'll take this value, update this, take this value, update this. And since we're using range queries, which it would basically mean either a bit tree or a segment tree, both work, and I'll show both in the implementation, we can actually, every time we reach a point, since we're going to be looping through, we're going to reach this point, we're going to update its corresponding place in the range query, and then we're going to query it. So we're going to find the value of DP, whatever this value is, and we're also going to update the value in our range query. And that way, as we loop on down, we're basically going to be able to find for any certain point what this value is. So we'll be able to find and update this accurately. And since we won't be going back to any old rows, this is basically going to store the sum of each column. So as we go down the columns, as we go down rows, every time we reach a point, so once we reach here, we'll update this. Once we reach here, we'll update again. Once we reach here, we'll update it again. And as we go down, it's basically going to store the column prefix sum for each point. And that way our 1D range query is able to be turned from this 2D to a 1D. And we'll do the same thing for the total range query and every color range query. So if I were to reach this point, I would update the total range query, and I would also update the color range query. So in this case, it would be updating the range query or the segment tree or bit tree for the color pink. So the time complexity of this is going to be ORC log C, and that's actually going to be pretty much fast enough. However, if we were to implement this directly, the space is going to be KC, which basically just means too much. And in order to optimize our space, we're going to add another optimization. We're going to compress our 1D range query array. And the way we're going to do that is, let's see, since the space is too much, when we look at this graph, we're going to realize that sometimes some columns are not going to have a certain color. For example, if we have the color blue, let's assume this column has it, this column has it, and this column has it. If we were to not compress, then it would look something like a 1D range query of size C, and then it would just have like maybe one here, one here, and one here. But in order to optimize it, we can basically compress it, so when we read in the input, we'll notice we only really have 3 columns for this color that we care about. So we're just going to compress it into a 1D range query of instead size 3. And then we can use mapping techniques in order to basically, every time we want to find this value, we'll just go here and then we'll find the corresponding place. So this column would map here, this column would map here. And that way, instead of having size C for every color, we have a much smaller size for every color. That's the basic gist of the algorithm. Let's go look at the code to see it in action. For this code, I'm going to be using a lot of if and else, because I'm going to be showing you both the segment tree implementation and the bit tree implementation. So I'm going to say if def new segment tree, and then else and if. And then so the part that goes in here is going to be the implementation for the segment trees, and then the part that goes here is going to be the implementation for the bit trees. So if you're coding with either or, you can just ignore this and then only paste or only type in the code for this part or only type in the code for this part. We're going to start off by defining a couple of variables. We're going to have n and then m as our mod, then the input variables, and then our grid. M and color vector are going to be used later on. We're going to read in our input, so that's going to be K, R, and C, and then we're going to resize color vector and M as they are vectors. Okay, so since we are going to be using either segment trees or bit trees, I'm going to have a seg or segment tree and then colors, or I'm going to have a bit tree for colors and then all colors. For our segment trees and our bit trees, we're going to be defining two different data structures. So for our segment trees, we're going to basically have our segment tree implementation, and this one is copied from the USACO guide, and it just has a standard template or a structure for segment trees. And then for our bit trees, it's just going to be another standard structure. So we'll have our tree, and then we'll have a couple different functions. So for both of them, they have the same keywords for the functions. So we have init, which is basically going to give the size, and then we also have update and query. So that's just going to update and query, and depending on if it's a bit tree or a segment tree, it's just going to follow the same standard code as for a bit tree or a segment tree in updating or querying. So query is going to take in the input of whatever index we're querying for bit trees, and then update is going to take in the index and then the value. Then for segment trees, we're going to take in the index and then the value, and then when we query, since for segment trees we have a start and an end, we're just going to input the starting index and the ending index. After we resize and then we create our variables, we're going to initialize all colors. And then what we're going to do is we're going to read in our grid. So this is going to be 1 based. I and J are going to be going from 1 to R and then 1 to C. I'm also going to make the colors 0 based, so I'm going to subtract, and then our colors are going to be from 0 to K minus 1. When we have our grid, we're going to input it into our grid, and then we're going to take our color vector C, and we're just going to push back J. And that's basically going to mean we're going to take our color, and then we're going to push back the column. And this is going to be the column prefix sum, or the 1D range query that we were talking about. So this is going to allow us to basically compress our 1D range query array. And in order to compress it, we're going to have a lot of duplicate columns. And so in order to get rid of these duplicates, after we read in our color vector and then we have our color with its columns, we're going to loop through. And we're going to sort it in order of the columns. And for each column, we're going to then update it into M. So we don't need duplicate columns, since once we compress them, if they're the same column, we're just going to compress it to point towards the same index. So what we're going to do is, we're going to have our value M, which is going to be up here a vector of maps, and M is going to have two parameters. We're going to have I and J, so I is going to be the actual color, and then J is going to be the actual current index, and then we're just going to, the original column index, and then we're just going to assign it the value of the new column index. And in order to find the new column index, since we're using a map, it's just going to be the size of this current thing plus 1. You can also just use a counter in order to find the current index. So after we've sorted our color vector, for every color, we're going to have Mij, where it's going to map, it's going to point the color, and then the original column, and it's going to give us the new compressed index. After that, we're going to initialize the size of colors I. So colors is basically going to store our different trees, or our range queries, for every color. And then the size, this is where the compression came in, is just going to be the size of Mi, so the M color. And then we're going to add 2 to the size. And this way we're not making a C-sized thing for every color, and it saves a lot of space. The next thing we're going to do is we're going to initialize by updating our first point. So we're going to update the first point 1 with the value of 1, since there's one way to get there. And then we're going to update it for both the all colors tree and then also the current color tree. And when we update that, it's just going to be colors and then the color in grid 1, 1. And then we're going to update it at this value index, and then it's going to be with the value 1. So the final part of our code here is just going to be looping through, and we're going to loop through with I from 2 to R, and then from J from C to R backwards. So this part isn't completely necessary, but when we look at this, since we are using 1 based, we're just going to go from 2 to R, from C to 2. And then we're going to assign X to the current color, and then if we're using segment trees, we're going to query from 1 to J minus 1, and then from 1 to this color minus 1, so this is just going to be our compressed index for our column. And then we're going to add M and mod M. And the adding M, modding M is just to make sure we don't go negative and we don't overflow or anything. And then for bit trees, it's pretty much the same thing, but since our query is a little bit different, we're not going to need our first element, and we're just going to query J minus 1 and then the new compressed index for the color, and we're going to add M, mod M, same thing. After that, for both functions or both types, we're just going to update the value in all colors. So we're going to update it with our DP value, which is just our answer, and then we're going to have it at index J. And then for colors, we're going to update it at the compressed index, and then it's still going to be our answer J. At the end, we're going to output the answer C, which is just going to give us the total number of ways to reach the bottom right corner. And that's the end of our program.